All right. Now, this problem makes a giant assumption. What is that assumption? What is the assumption that is made by this problem? If you are at home and you know it, just blurt it out. If you're here and you know it, just blurt it out. What is a giant assumption made by this problem? And it may not smack you in the face, but it might also just jump out at you. Might we take a guess at the giant assumption that's made? Morgan?
Is it that the two people are male and female and not both male or both female?
It's a good assumption, I guess. If we take into account that maybe if they're both male, they're not going to make babies or whatever. It's a good one. I'm looking somewhere else though. Mal, were you going to say something?
I was going to say that like the frequency of the allele doesn't change.
How would you know that's a big assumption?
Because it's assuming that.
It says so, right? And so you're right. That's actually the big assumption that I'm talking about here is that this problem assumes that the frequency of this allele does not change as the population grows. All right. So let's go back to the basics, some of the first stuff we talked about with Hardy-Weinberg. And it's some of the stuff that I've skipped over for this reason, because I think it falls better in this particular set of sequencing. Okay, the Hardy-Weinberg theorem states that the frequencies of alleles and genotypes in a population's gene pool remain constant from generation to generation. Meaning that if we have a population like this, and we have a value for P that worked out to be 0.95, and a value for Q that was 0.05, that if the people in this population mated and had, let's say, 100 babies, which is a lot, that all of the alleles in the following generation, if you broke them down and looked at them, would have the same allele frequency. Okay? That's what Hardy-Weinberg is assuming, and that's what this statement right here also assumes. Okay? So this problem here basically is stating that it is assuming that this population is in Hardy-Weinberg equilibrium, as they would say. That's how you would state this. Okay? Now, why is this a big assumption is the question. Because in the next slide here, it states that there are 5 conditions that have to be met for a population to be in what we call Hardy-Weinberg equilibrium. Okay? And if a population is in Hardy-Weinberg equilibrium, it means that the allele frequencies do not change from generation to generation. Also, this means that there is no evolution occurring in this population from generation to generation. If the allele frequencies do not change, then there is no evolution. Okay? Now, so what are some of these stipulations? What are some of these conditions that have to be met for a population to not be evolving? They're listed right here. The population has to be extremely large. There can't be any flow of genes into or out of the population. Can't have any new mutations in this gene pool that just pop up. Mating has to be random in the population. And then there can't be any natural selection in the population. So then I go back to this problem, which states that we're going to assume that this population here is effectively in Hardy-Weinberg equilibrium. Is that true? Is this a Hardy-Weinberg population? Gwyneth, you're shaking your head. How can you tell?
It's really small.
Okay, that's a big giveaway. That population was 20 people, so it does not meet that stipulation. Okay? How else does it go against this particular set of conditions? Nick, what do you think? No? Sandra? Yeah, think about the population. They're humans, right? Humans don't randomly mate. Like, random mating would be like, if you wanted to have a kid, you go out in the hallway, you spin around and you point at somebody who you could theoretically have a kid with, and you go have a kid with them. That's random mating. That doesn't happen with humans. It's weird, right? We would classify that as weird behavior. So that would be the same here, right? Those people on that island are not just going to go get together on like a Friday night, spin around, and the first person they see make a baby with. This is not going to happen, right? So they don't follow the random mating. What else? What other stipulations do they not follow? There's at least one more, possibly two. Think about the population that's described here.
No natural selection.
Yeah, no natural selection. Why would you say they go against that one?
They're human. They know how to survive and stuff.
Well, that would not be the case. So when we're talking about no natural selection, that would mean like they are alive. That the environment can't kill them off effectively. But in this case, what disease is in their population? Cystic fibrosis, okay? So in this case, natural selection, if anybody actually had cystic fibrosis, they'd probably die, which means natural selection is going to pick them off, okay? Which means there's not no natural selection. It means there actually is natural selection in this population, because natural selection will pick off anybody with cystic fibrosis, possibly. Because they're on a deserted island out in the middle of nowhere, right? The only one we know for sure, for the most part, that they actually do qualify is no gene flow. They're on the middle of an island in the middle of the ocean, okay? There's not going to be new people coming into their population. There's probably not going to be anybody leaving the population. It's just them. So there's no gene flow. We can't even say that there's not going to be no mutations, because that's just what happens. Mutations happen. Okay? They're random and they're rare, but they do happen. Okay, so we can't even say that. So, you know, the problem makes this assumption that they're in this Hardy-Weinberg equilibrium, but they're probably actually not. If a population is not in Hardy-Weinberg equilibrium, what is happening? What will happen to the allele frequencies if they don't meet all of these? What will happen to the allele frequencies of this population? They change, right? And what do we call change over time? Evolution, right? So that's what's happening. If a population is not in Hardy-Weinberg equilibrium, chances are it's going to be evolving in some way, okay? Small evolutionary changes, meaning sometimes just allele frequencies changing over the course of generations, but that's still technically evolution, okay? Now, in this previous slide right here, big red words down at the bottom says hypothetical, right? This is a hypothetical thing because we just verified that really, if you look into it, no population on the face of the planet is actually in Hardy-Weinberg equilibrium. But that's what we want to make sure of. We want to make sure, okay, is this population's allele frequencies, are they changing over time? If they are, then we know that they're evolving. We can assume that they're not going to, but when we eventually do see them change, we know that those populations are evolving. That's why we can say that this is used as a benchmark to measure evolution against, okay? So this is one of the things that I wanted to spend time on, was the context with which we use these 5 conditions for non-evolving populations. Now, if a population did happen to meet these, it would be very, very rare. Okay. And it would mean that their population is not evolving because all of these things here are going to contribute to keeping the allele frequencies roughly the same. Very, very close anyway. Okay. So that's the context I think that you needed to understand what was going on there. All right. So I think we'll go ahead and transition here. We're going to take a few notes. We're going to continue them, I think, tomorrow. I would love to get some PTC paper tomorrow as well. I don't know if I can find any. I don't have any left. I've got to talk to the other teachers, but there's a short video that I'd like to watch that deals a little bit with Hardy Weinberg. I can relate the two, but it deals with population genetics as well. So we'll pick that up there, and then we'll continue with some of the notes, and then we'll see what happens Wednesday. I'm not real sure yet. Okay. Okay. So before we jump into some more of the particulars of populations evolving, I thought it was important here to include, this is a very short section, but to include the importance of mutations in this entire process. Mutations are kind of the original source of genetic variation, which we've talked about before. And they change the existing genes into different versions that that weren't there before. And sometimes in super, super rare cases, you can create a set of new genes that will code for a brand new trait that was never seen as well, okay? And usually these mutations happen without any of us really knowing. From time to time, we get bad ones. For instance, point mutations, usually pretty harmless. They probably happen a lot of the times in our junk DNA. It's just a substitution a lot of times of one single base pair for another. But every now and then, you run into certain point mutations that can significantly impact the phenotype. For instance, a point mutation example of one is sickle cell anemia. It's a substitution of one base pair for another that if you get it, you could possibly die from sickle cell. It makes your life kind of crappy, right? If you don't die from it. So you get these instances where the mutations sometimes are really, really bad. Other times they're innocuous. They don't do anything at all. Sometimes you get these situations where they're good. Maybe like making all sorts of cool looking horse colors, right? And I threw that up there for, you know, color value, both literally and figuratively. Brighten up the PowerPoint and give us a talking point. The coat color that you see here on these horses that are all the same breed is due to random mutations that happened maybe in the gene that coded for their coat color. And so they get these mutations and then they can pass them on. It is the phenotype that is acted on by natural selection. So I don't know if that particular phrase or statement is anywhere in your notes, but I think it's an important one to understand that it is the phenotype that is acted on by natural selection. If these horses get a specific phenotype that doesn't allow them to live in their environment, natural selection is going to pick them off, okay? So these mutations that happen at the molecular genetic level are really, really important because they change what the animal looks like, and that in turn affects how they live, and it ultimately affects how they breed, right? Yeah, I'm nothing really necessarily needed up with these top 2 bullet points here, but I do want to speak at least a little bit on the mutation rates and why we don't see this as often in human beings as we do things like microorganisms. We don't often, as human beings or higher order organisms, we don't see these crazy brand new traits, these brand new phenotypes, these new renditions, but like we don't see green hair, right? it's not something that naturally comes out of the mother's womb. They're like, oh, a kid grew up, has got green hair. We've got red hair, we've got brown hair, different versions of black, dark brown, blonde, all these different shades that we have. Winston blue or pink or anything like that, not yet anyway. And one of the reasons for that is because the mutation rate in higher order organisms is really quite low. It's 1 in 100,000 genes per generation that we actually get some kind of mutation that causes either a really, really terrible disease or some kind of trait to be different from what it would be. Okay, so the chances of a brand new trait somehow popping up that causes green hair when you're born is really, really low. Okay, one of the main reasons for that is because animals and plants have really good mechanisms for detecting mutations and then fixing them. Okay, microorganisms do not. Microorganisms like coronavirus, if you want to call that an organism, it's not really living, but the thing mutates all the time. I saw a chart a while back at the very beginning of the pandemic that outlined the dozens of different mutations that this thing has gone through, and that was within 3, 4, 5, 6 months, something like that. And now, it's kind of settled on this new mutation that it has allowed it to reproduce rather effectively, right? These new variants found in, right now, it's kind of running rampant through India, the one from Great Britain, okay, that one, and then the one in South Africa. They're a little bit more dangerous and contagious, and we just don't see that type of mutation rate. And one fact I think I saw is that like 1 in 10,000 genes per generation. So an order of 10 times more when you're looking at microorganisms. So you see a lot of the antibiotic resistant bacteria and viruses and things of that nature come about a lot more often because their mutation rate is quicker, right? Now, that's all fine and dandy, and we can say that mutations are the original source of this variation, and they are. But sexual recombination really has a more drastic effect on the adaptations that are possible. More specifically, sexual recombination really has a more drastic effect on the combinations of traits that you can have. Okay? Whereas maybe in a population, somebody with brown hair and blue eyes was found more attractive, and so they got a better possibility of being mated with, okay, than somebody in another combination of mutated alleles. So we find that sexual recombination actually is what makes the mutations a little bit more effective in the wild, okay, at having the individual either survive or not and then be able to reproduce afterwards. And so what we have to realize is that it is the phenotype that natural selection acts on when we think about that. So just keep all the mutation stuff and sexual recombination stuff in perspective. Okay. Section 3, we're going to wait until tomorrow. I'm not going to jump into that just yet. See how far we get tomorrow, and I think we'll just kind of continue through this and hopefully get through section 4 as well. And then maybe the last section I'll do on a video, and we'll see where it goes. But we are going to watch a short video tomorrow, about 20 minutes long. It's actually pretty interesting. Maybe if you want to bring some broccoli. I don't know. Maybe I'll bring broccoli. Is it right to feed you guys things during a pandemic? Probably not. Frowned upon.
So, if we used to do like.
It's got to be individually wrapped, right? Like I'd have to go to like Fresh Time or something. They'd have to wrap it.
So, what they did at theater is.
All right, you guys can take off. See ya.
If you have one person serving it with gloves, then you can individually